Okay, so thank you very much for the introduction and also for the invitation to give the talk, because actually it was your idea. Okay, so the talk this evening will be about the dark universe. So we will survey a few things that tell us that we don't know basically anything about the universe today. So this is actually very exciting. We have here a pool of young researchers that this means that they have something to do for the next 40 years. So it's nice when you have problems to solve, right? Actually, there is a very nice definition of physicist. Here we are, most of us are physicists. And the definition is that a physicist is somebody that tells you, solves a problem that you didn't know you had in a way you do not understand. So I will try to actually show that this is the case also when we study the universe. So let's start very dramatic. About 95% of the universe is actually dark. We know that there is dark stuff there, but we don't know what that is. And by dark, maybe it's better to specify a little more, because dark means non-luminous. Most of what I will say is actually referring to something that does not really interact significantly with what we call light. Therefore, we infer the presence, but we don't see that stuff. But also dark means that we do not understand this stuff at the fundamental level. So it's actually a puzzle. We have two kinds of darkness in the universe. One is dark matter, and the other one is dark energy. And the two big questions are not only, we know that they are there, I will try to convince you that actually we have ideas that they are there, but the questions are, what is the mass that gravitates but does not shine, and this is dark matter, and why is cosmic expansion, the universe is expanding, why cosmic expansion is actually accelerating and not decelerating as we would expect. And this is what we call dark energy. So everything starts from something like that. What we know from the far universe is actually brought to us by something. And this something, first of all, is light. So we look at light in the sky, and we see basically the light emitted by something that can emit light, so stars. In the universe, we have a lot of stars. These stars aggregated to form something which we call galaxies, are something that are bound together, stars that stay there and move around. And galaxies tend to cluster to form what we call galaxy clusters, which are even larger objects. Here you have some numbers that tells from how many stars we have in a galaxy and the size and how many galaxies we have in a cluster. So these are very large objects in the universe, really huge. This is maybe one of the deepest, as we call, images of the universe is from the Hubble Space Telescope Deep Field Camera, where we see something that is actually emitted light at the very early stages of the universe. These are actually, some of these objects have actually emitted light about 10 billion years ago. So we can actually map through light what's outside there. But then we have a number of problems, because we see objects through the light that they emit. But from the behavior, the characteristics of these objects, galaxies, clusters of galaxies, the whole universe, we infer that there is something more. And the first example is canonically referring to what we call rotation of spiral galaxies. So this is an image from the galaxies taken from above. This would be similar to what we would see if we could go up and see our own galaxy from the top. And we see that actually the galaxy has arms, and there's a bulge at central high density of stars, because we see the light of the stars. So there is a lot of light there, so a lot of matter that emits light, and then it decreases as far as we go. These stars in a spiral galaxy tend to rotate around the center of the galaxy, to at least to first approximation, and therefore we have a system which in a sense could resemble the solar system. We have most of the mass concentrated in the center, And we can measure the velocity of rotation of the objects far from the center. And we know how these things behave. And we also know that the farther we go from the center, the slower the objects rotate. And from the laws of motions, we refer to Newton's laws of motions, and in this context to what is called Keplerian motions, we can, in principle, we could determine the mass of the sun by looking at the motions of the planets on the orbit. No, it's not, because gravity attracts masses, and therefore, depending on the velocity, you could either, if you throw something here on the Earth, come back to the Earth if the velocity is too low, be ejected from the Earth if it's too high, or stay in orbit. And depending on the energy, you can have a circular orbit or a elliptical orbits. These are bound orbits, so the object continues to rotate around that. And depending on the velocity, the size of the orbit, we can determine the mass of the object that is actually determine the gravitational field. Here we have the first problem, because if we go back to our galaxies, what we find is that the farther we go from the center, we should expect a decrease in the velocity. This is the velocity, the speed of rotation, as a function of the distance from the center. We should see a decrease, because at some point, if you take a circle around with the big radius, most of the mass is there. So it's like the sun and nothing else in between. Not exactly, but very similar. And this is even more true if we go farther, because we see less light, so there are less stars. At some point, when we go very far, we don't even see stars, we just see gas, hydrogen gas. Therefore, from some radius on, from some distance on, we should expect what we see for the motions of planets around the sun. This is what we would expect, but this is what we see. We see something that the velocity of rotation does not decrease with distance. And this is actually a problem, because we have the law of gravity. They come back to Newton. Well, we have general relativity, which is even a better description of gravity, but motions here do not require necessarily general relativity to first approximation. We would expect a sort of Keplerian-like velocity decrease, but we don't get that. And by far, the farther we go from the center, the larger is the discrepancy, and that's huge in a sense at some point. This is, in a sense, not that different. Maybe we can understand something about the system. It's not that different from what happened actually in the 1800s, where gravitational anomalies, what I describe is a gravitational anomaly, something that moves contrary to what we would expect with the normal gravity. And Leverrier actually discovered the existence of a planet, Neptune, by studying the anomalies in the motion in the orbit of Uranus, another planet. There were deviations from the Keplerian motions, and he was able to determine that this discrepancy between what you expect and what you see are due to the fact that there is some object that we don't see because it's so faint that we don't see the object. The light that comes to us is not enough to see. This was actually discovered. Leverrier predicted the existence of the planet, also the motion, because you can trace that by looking at the other object that fills that one. And it was discovered, and that was Neptune. So we can use gravitational anomalies to discover something. It's a discovery tool. Actually, Leverrier also tried to describe another anomaly that was present. At the time was an anomaly, and the fact that the orbit of Mercury precedes, let's say, there is a precession motion. So the plane of rotation rotates together with the planet. And he tried to do the same. So he predicted the existence of another planet, which does not exist. Vulcan does not exist. The explanation of the, let's call it anomaly, motion of Mercury was then correctly explained by general relativity, Albert Einstein's general relativity, but this came later. So we see that gravitational anomalies can be a very good tool to discover something that we don't see because it does not emit enough light to see it, but at the same time can also be used in an incorrect way. So we must be careful. And this is exactly the situation that we have today with the galactic rotation. Since velocities are higher than expected, a simple explanation is that there is more mass than what we see through light. More mass, more velocity, therefore we infer from here that there is much more mass than what we see. This is what we call dark matter. And this is actually the case for any galaxy that we observe. A second place where we see that there must be something that bounds, glues the system more than what we would expect if the system would be made only by something that emits lights, are galaxy clusters. This is an image of a galaxy cluster. We see here not stars, but galaxies. There are stars inside the galaxies, but there are many galaxies, and they are in a relatively small region of space, which is not small on normal ground, but they are not distributed homogeneously on space, so they are clustered. This is called galaxy cluster. The problem is analogous, even though it's a little bit different the way it's inferred, because these are not orbital circular motions, but the point is similar. The galaxies move, we can determine the movement, measure somehow the velocity at which they move, and we can determine how much mass we expect to have if only what emits light produces the gravitational field. And we found that the velocities are too high. Too high velocity, the system should evaporate or disperse. If you calculate how much time it would take from the system to just disperse and not be that clustered, it takes much less than the age of the universe. So this means that it's improbable that it's just a chance. You just walk around randomly and you are all in this room. You are not all in this room by chance, no? There is a meaning because you are here. Very likely there is a meaning why these galaxies stay close to that. And again, we can interpret that saying there is more mass that we don't see, it does not emit light. Can be even several times more than the mass that we ascribe to what emits light. So from light we see something, but the something that we see is not enough to explain how that system behaves. And again, this actually is called dark matter again, because it should be the same. I mean, the hypothesis that the same dark stuff that is responsible for this behavior, it's natural to think that it's the same dark stuff that is responsible for the behavior of the galactic rotations. These are sort of two historical ways of determining the fact that there is more mass than what we see, but nowadays more modern ways are present. For instance, one very, what happened? One very common way today, it was not used before, I mean, these last 30 years, is to rely on what is called gravitational lensing, which is just the fact that, maybe let's go here first, the general theory of relativity, which is actually a theory of gravity, and there is a famous sentence that I think it was made by Wheeler. It says that space-time tells matter how to move, matter tells space-time how to curve. Not only matter, even energy, because the spatial theory of relativity tells that matter and energy are the same thing. And the general theory of relativity, therefore, says that concentration of mass or concentration of energy doesn't matter. It bends space-time. We live in space-time. Everything has to move along the space-time, cannot go outside of that. And therefore, if there is some bending of the fabric of space-time, light, even light, has to bend. The prediction of gravitational lensing was actually what made Albert Einstein a rock star from one day to the other. Because this was predicted by Einstein, And very soon, in 29, the theory is 17, but this is 29, this effect was discovered by Eddington, making a measurement where you look at the position of the sky of a star, and what you see by comparing the position in the sky of a star when the sun is not along the line of sight, so when the sun is not there, and what you see apparent position when the sun is close by the trajectory, you can see that there is a mismatch between the two positions. And this mismatch is due to the fact that light has to go on curved pattern. So you have that a star that has a real position here shines light. And if there is not the sun in between, you should see at a given position, this is the Earth as you see, no? If there is something in between, the light bends, but then we interpret the light coming from straight on, and therefore we associate an apparent position which is not there. If you do the same measurement of the position of the star when the sun is there and when the sun is not there, you can see this change in position, because when the sun is not there, you see that star there, and when you repeat the measurement when the sun is there, you see the star in a different angular position in the sky. The point is that you need the star along the line of sight, and you can do that only during day, because during night the sun would not be along the line of sight. So the only way to do that is during total eclipse. And so in 29 there was a total eclipse, and Eddington managed to show that. Apparent position and true position of the star, the position of the star was moved with respect to what it was measured 6 months before when the sun was not there. And therefore this was the amount of deflection was exactly what was predicted by general relativity. So this was a huge success for the newly born theory of Albert Einstein. You see, Einstein theory triumphs. Then I don't know what's this, a book for 12 wise men, I don't know exactly what does it mean, but this was one newspaper of the time. This means that as light goes through a glass, distorts images which are of objects in the background, or even the position is seen in a different position from the real one, the same occurs if the lens is not an optical lens, but is a distribution of mass. Therefore, what we can do is the following. We have a galaxy farther away, and we have some distribution of mass between us, the distribution of mass between us and the object, for instance, a galaxy. The light bends, so there is a light from one point of the galaxy, a light ray goes in one direction and bends toward our point of view, and the other one gives another bend. Therefore, the same point there can be seen in two different points on the image of our detector. And we see distortion. I don't know if you can actually see it here or here clearly. Here maybe it's better. But we see a lot of distorted images. This is the image of a single galaxy, which should look like that, but it's seen as squeezed. We have another arc here, another arc here, two arcs there, another arc there. So these are images of distorted objects which are farther apart, and there is mass between us and them. And more mass means more bending, less mass means less bending, and therefore we can infer how much is between us and them. For instance, this is a cluster of galaxies, so how much is the mass is in the cluster of galaxies by looking at the distorted images. It's not easy, but in principle we can do that, which is actually what we do. Gravitational lensing is actually producing different types of effect. Suppose that you have galaxies far apart, and between them and you put some mass, which is our gravitational lens, so light has to bend. When we are in a specific situation where the deflection and distortion is huge, we have what is called strong lensing regime, and a single galaxy can even be seen as a complete round circle or arcs, part of the full. Or, depending on the geometry, even relative position, we can even see multiple images. These are multiple images of the same, one of the famous one is this one, but also the other one are very similar, where actually these 4 images are the same far source. It's a quasar, active galactic nucleus, very far in the universe, and the light passed through the gravitational lens, producing 4 images of the same object. This is called the Einstein cross, because it's actually like to see a single image positioned at the corners of a cross. Actually, since the path of light is different, you even have a time delay between the different images. There are even images nowadays, not this one, where you see, for instance, there is a supernova exploding, and if the light goes through a gravitational lens, you can see the image in one point and another image appearing maybe one day later. That's amazing. So you can even use the fact that you have time delay, and therefore from that infer information on how much you have, how far is the object, and so on. But these are special situations. More normally, you have that the light goes through maybe a huge number of deflections. Everything, even you, deflect light. Of course, very, very little. But if we have light that started 10 billion years ago from a very far distant galaxies and goes through the whole universe and reaches us, it can encounter a lot of galaxies, clusters, and everything else, distribution of mass in the universe, and be continuously deflected. If we have a single object in between, we have a single deflection. And if this deflection is small, not such that you produce these striking rings or multiple images, what you have that what would be a very nice galaxy seen from above like a circle. Okay, typical physical approximation is first approximation, everything is a circle or a sphere. And you would see 2 different effects. One is called convergence, and it's actually the fact that you magnify or demagnify the image. It gets smaller or larger. Think of a lens. When you use your glasses to see, you need to, for instance, magnify an object. And this is actually happening. This does not help that much, because since you don't know the characteristic of that galaxy, difficult to know if it is brighter because it's brighter by itself, it's brighter because light has been actually lensed. The other effect is that you distort the image, and to first approximation, the circle becomes an ellipse, and this is called shear. No? You deformed it. From a single object, it's difficult to say that it was not an elliptical galaxy from the beginning, but if you have many objects in the background, weak lensing, this is called weak lensing because it's not that strong as that one, determines a pattern for the distortions. So you see here, this is one way. You see that the images have been distorted, but also aligned in a specific way. So they shear. This means that from looking at many objects, typically this is done through statistical analysis or correlation analysis, you can determine the fact that there was a mass in between us and the objects of a given size. Okay, so actually shear has 2 different ways of showing that, and this is actually something that is studied significantly today. Just to show you a very striking lensing, strong lensing image, I always like to show this one, which is called the Smiley Galaxy, which looks to me very much like the Cheshire Cat of, what's the name? Alice in Wonderland. Well, the cartoon, of course. These are two galaxies, I think, but you see this, which is the smile and the face. These are images of strongly distorted, farther away galaxies. Then the alignment was so funny that we see these kind of things, which looks like, but this is something of our brain, you know? But the fact that we have a single galaxy that was distorted in this way, it's not that different as when you look through the bottom of a glass, right? You have this strange roundish thing. Of course, the physics is different, but nevertheless, you can measure that. Through strong lensing, but also weak lensing, you can even map the unit. This is a sort of reconstructed distribution of mass between us and some far field by looking at images of galaxies very far apart. And since the light is actually going through many times, you can, it's very complicated, but make a map of the distribution of mass between you and that. And then compare to the distribution of light. You see light, but you have much more mass that you infer from gravitational lensing than what you see from light. Another maybe, well, it's not actually the last example, is that we can even combine techniques to some extent. And one way of combining is actually what happened with what are called colliding clusters. The most famous is the guy on that side, which is called the bullet cluster, and this is another one which is similar to that. The main point here is that you have two clusters of galaxies colliding. The cluster of galaxies, if there is dark matter, is supposed to have a lot of dark matter and some gas, normal hydrogen. When they collide, what do? Well, hydrogen has to interact. If you compress hydrogen, it gets hotter. So what you can do is to measure in X-rays the hot emission of light, which is a tracer of something which is hot. Through gravitational lensing, you can measure how much mass there are in these two colliding clusters and where the center of mass is. And what comes out is that the gas is concentrated here and here, the red one. The blue one is one blob, dominating blob here, and another blob here. And therefore, in this case, it seems that we have that the dark matter mass and the gas are offset one from the other. And the interpretation is that the colliding objects, dark matter did not interact and went through. So this cluster here, this mass concentration here, was previously there and vice versa, while the gas is compressing and therefore produces hot, it becomes hot and produces X-rays. We even see a sort of wedge like you would have when you shoot a bullet. What happened? I don't know. When you shoot a bullet, no, it's a shock wave. And therefore, this is called bullet cluster for that. This tells a number of things, that the most of the mass is here and here. It's much more than the mass in the gas. The two are offset, and this is actually here because it's a compressed gas that interacts. It's actually dissipative. But dark matter goes through, and therefore it does not interact significantly. It has something of this substance, much less than what actually. It's weakly interacting in a way. This is similar because we have the hot gas here, and the mass is all concentrated here. You have much more mass here and here than there. This is hot, therefore this is hydrogen. This is cold, and therefore it's not. And this means, again, it's compatible with the interpretation that I have much more mass, which is weakly interacting, going through, and the gas compresses and heats up. As a further and maybe last example, I show you a video which was actually made by putting in a video galaxies observed by what is called the Sloan Digital Sky Survey. It's a survey of galaxies. You measure individual galaxies and the distance from us, and then you put them in space, and then you make a movie. The movie is just how we would see the distribution of galaxies if we could move very far between them. No? We see it's like we have regions where there is more concentration of galaxies. These are clusters of galaxies. Regions where there is not much mass. and the regions which are actually filamentary, and regions which are sort of void. You see here we have a cluster of galaxy, and so on. Here it's made in a nice way to show a movie, but this tells us how the universe is actually, how matter is distributed in the universe. Clumps of matter, we only see light, but if we take that cluster and we measure the total mass, we have 10 times more mass than the mass of the light that we see. And therefore, this tells us that the universe is strongly anisotropic and has this fancy distribution of halos, clusters, filaments, and voids. This is how our universe is actually out there. This is another way of seeing the same information but projected. This is only a slice of that movie, only a selection of galaxies of that movie in space. And we see exactly what I said. The distribution of galaxies have large voids where there is not much mass, filaments joining much more dense regions, which are clusters of galaxies. So this cosmic web of filamentary structure of the universe, of at least a recent to some extent universe, is actually very informative because it tells us also how matter is distributed in the universe. And how matter is distributed in the universe can help us in understanding what dark matter is. So we have this first big problem in the sense that we have, I try to show a large number of evidence that there is mass in the universe which is more abundant than the mass that emits light. And the question is, where does it come from and why it's distributed like that and what is that, of course. This is the problem. So maybe to try to give an answer to the problem, we need to put another piece of information in the game, which is the fact that the universe is expanding. We know that since 100 years, this is the so-called Hubble law, even though Lemaitre already discovered the Hubble law a few years before Hubble. He published that in a paper. Well, actually, he wrote a paper where the expansion of the universe was present in the paper. But when Hubble actually made the measurement and published his own paper, Lemaitre published his own paper omitting that part. And when people said, but why you didn't put everything? You did that 2 years before. And he said, well, because Hubble already said it much better than me. So, very humble. But now the Hubble expansion law is called Hubble-Lemaitre. It was decided by the Astronomical Union. The point is the following. Expansion of the universe is nothing strange, just the fact that if you take two random galaxies in the universe, they tend to get farther apart as time goes on. We are moving apart, for an instance, from Andromeda galaxy 70 kilometers every second. The point is that this is not very difficult to notice because we are 2.5 million light years away, so it's not a lot, but it's an effect that is measurable. And the expansion of the universe tells one thing. If we do, like in a movie, we go back in time instead of going farther in time, if you have matter distributed in the universe and the universe expands, so each volume after some time gets twice as large, but you don't produce or destroy energy and matter, the density goes down. So if you go back in time, the density goes up. So you should expect that at high times, the density of matter in the universe was denser. We are here today with a given density, and if you go back, the same stuff is pushed in a smaller volume. If we continue this idea farther and farther back in time, we should expect that at some point that the size of that volume becomes so small that you cannot have any longer individual planets, individual galaxies, individual objects that we see today, because the space was smaller than that, okay? So that matter should have been more compact and less organized. To a point such that, think also of compressing matter, it gets hotter. So if you continue to do that, suppose that you do not have any longer the galaxy, you must just have your hydrogen or whatever. And you compress even more, it gets hotter, and hotter. So if this actually goes back to a point, which is actually just a fictional point, because actually we don't know what happens there, but we call it Big Bang, so the model of universe expansion, the simplest model, tells us that the universe expands with a given law that we can determine and has a singularity, as we said, at some time called t equals 0, which is called the Big Bang. We don't know exactly what's happening there, but we can pretty good model what happens some infinitesimal fraction of second from that moment on. The universe for sure couldn't have a galaxy. Therefore, needed to be just hot, dense matter, very homogeneous in a sense. This was the idea that a few people put forward in the 40s. And from this idea, we have that the universe, go again forward in time, was very hot and dense. But if you then go now forward, you have a very distribution of hot and dense. It's a plasma. The plasma now going forward in time gets colder and colder. Now you need to reach a moment in the universe when actually it's more favorable for the universe to be not a plasma, charged plasma of electrons, protons, and even other things before. But it's more favorable to have that electrons and proton become hydrogen atom. It's neutral. This moment is called recombination, and it's the time when the radiation, which was actually interacting continuously with the electrons and protons, but mostly the electrons, in the plasma, does not find anything else to interact with, because matter becomes neutral. And then for this radiation can travel up to today. And this is called the cosmic background radiation, which today is measured in as the most abundant density in the microwave band. This is actually a quite natural prediction of a universe that had to be quite dense and hot and cooling down. The temperature of the universe when this happened is similar to the surface temperature of the sun, which is not that strange because the sun is actually a plasma inside and then the density goes down. The point is that if the universe was very homogeneous and perfectly homogeneous, I can have this release of the cosmic background radiation, but that radiation should have the same temperature in any direction. But even the distribution of matter should be so homogeneous that nothing happens. You would not form even a galaxy. This means that the fact that we have galaxies here is a fact that the universe had some small fluctuations in the density. Very small, but gravity is attractive. So if you have a small over-density, it starts to eat matter from the surrounding. And we have 14 billion years here of time to form what I showed before, to form these structures here. This is actually due to very tiny fluctuations in the early universe that then grow in time from some point on and then start to aggregate. If this is the case, we can test that. Because if this is the case, not only the matter needs to be fluctuating, but also the temperature of the universe itself. And depending on what's in the universe and how the universe is, you would have that if you have a perturbation, let's take two different types of universes like two fluids, and you perturb them, you actually produce like waves. At some point, these waves, where actually you have more dense matter or less dense matter. More dense means hotter, less dense means colder. The radiation leaves that and does not interact anymore. And this means that the information of the hot and cold regions is preserved. And this reaches us today. This is the cosmic background radiation, which was actually discovered by Penzias and Wilson in '64, and then mapped the full sky by the Kobe satellite in '92, measuring a perfect isotropic distribution of temperature. The temperatures were the same everywhere in the sky, except at the level of 1 part in 1,000, what is called a dipole anisotropy. One region is hotter and the other one is less cold, because we move with respect to the reference frame where the temperature is isotropic, because we move together with the sun, together with the galaxy, and so on. But at a higher level of anisotropy, if you remove this structure, you start to see fluctuations at a level which is 1 part in 10 to 5 or 10 to 6. These are imprints of the fluctuation that I was telling you. And nowadays, these red and blue points, this is a Planck satellite map of these are fluctuations. And from the information of the fluctuations correlating two different points in sky, so how much correlation I have at a given angular scale and another, and so on and so forth, we get some, this is a little bit technical, but we call this called the power spectrum. But from this information, we get a lot of information on how the universe is. Where this peak is, it's a measure of the geometry of the universe, and the universe is geometrically flat. The relative size of the second and the third peak tells us how many baryons we have, so how many normal matter we have in the universe. This third peak is influenced by how much dark matter we have. So this is a sort of Rosetta Stone of the very early universe. This radiation was released 300,000 years from the Big Bang, and now the universe has 14 billion years. Therefore, it's a probe of the universe when it was very, very, very hot, or at least hot enough. And from this, we again find that we need dark matter. Otherwise, this fancy structure, that is what is measured, would not look like that. It would still look with these peaks and those, but nevertheless, not positioned in that way. And therefore, we have another information, the fact that the universe is there. Now I don't know how much time still I have. 5-ish minutes. Okay. So if now we think about a moment, we had a universe which was very hot, right? Very hot means that every particle that was in the universe could collide with other particles, like in a plasma, with high energy. And the farther we go, the energy was higher. Therefore, in a sense, the universe was like a particle accelerator. Particles in the plasma, and for sure we had what we see today, protons, electrons, neutrinos, photons, could interact between them, but if they could interact at very high energy, they could produce particles with high mass. Same principle we use in accelerators today, accelerator physics today. So if we go farther enough in time or in temperature, we could expect that these interactions could actually have produced even heavy particles, and these heavy particles could be what is called now dark matter. Then, from a very homogeneously small fluctuation, after the CMB recombination, you start forming structures because gravity is actually attractive, and therefore, at least in this regime, and therefore, where you have a little more density, that grows, and you form a cluster or a galaxy. And this is exactly what we see in theoretical models. This is a numerical simulations of a gas that starts very, very early in the universe. It's homogeneous, and then as time goes on, it starts creating exactly those filamentary structures with big voids and very dense regions, the light colors, in the universe. And how many of these you form, and on the scales that you form, depends on the type of the dark matter. If this dark matter is actually something that interacts weakly, if it is something which is heavy or light, you can have different possibilities. And the information compared in theoretical models, this is just universe expansion and gravitational instability and collapse that forms the structures. It tells us that dark matter needs to be something that is actually what, as we call, cold. This actually goes through what is called growth of structures. So how the structure grows, the structure that in the end will be galaxies or galaxy clusters, the way they grow, we have two things: expansion of the universe and collapse to form structures. Now I don't go through this in details, but growth is actually very sensitive to what actually we have in the universe, therefore, how much dark matter we have. We have another problem that maybe I can skip unless there are questions, which is actually the problem of dark energy, which is a completely different story. So because in order to maybe make a conclusion to what I was saying, is that I reviewed this part. We know that about 24-25% of the total energy budget of the universe is made by dark matter. The stuff we are made is only 5%. And then we have about 70% of this strange thing that is called dark energy, that is actually completely different from dark matter, does not form structures. But I might maybe say a few words to conclude about do we have ideas on how to explain what dark matter is. I didn't tell you in details that dark matter cannot be standard stuff, cannot be something related to what we know at the fundamental level of nature. This is the complete content of the standard model of elementary of particle physics. Nothing here can explain dark matter, either because it's charged or interacting strongly, like this object here, or charged does not work. We said that the bullet cluster tells us that it does not interact significantly. Neutrinos are too light, they do not work. And most of these particles decay. It cannot decay the dark matter particle if it is a particle, because otherwise it would go away. I mean, the longest living particle in this plot, apart from neutrinos, which are supposed to be stable, and the electron, but the electron does not work. Neutrinos do not work. Anything else decays. Therefore, well, the photon, but cannot be photon, is even lighter, and it's not. We said that dark matter does not interact with light. We don't expect its light, right? So the idea is that you have two solutions. Since the way we infer the presence of dark matter in the universe is gravitational, we have gravitational anomalies. Maybe the problem is gravity. So we do not understand gravity, which is at the moment the theory that we all use is general relativity. There are plenty of ideas. The idea that we can modify Newtonian dynamics in order to explain some of the problems like rotation curves of galaxies works very, very well at the galactic scale. The problem is that it has some problems at the cluster scale, and it has difficulties actually to explain lensing, structure formation, and this is a theory which is actually not theoretically fully included technically in a covariant theory of gravity. It's a law, it's a limit, so it's not clear how to include that. But there are attempts using different kind of modification of general relativity. The other part, which is very much studied, is the fact that it's a new particle, but it cannot be in the standard model. Therefore, here we open up a lot of possible ideas of different type of particle that can be heavy, can be light, can be some strange type of neutrinos, can even be some strange types of photon which are not the photon, the normal photon. They might need extra dimensional space dimensions. Even primordial black holes could be. It's not a particle, but it's an option. So black holes that are formed in the early universe If they are too light, with a mass smaller than the mass of an asteroid, they would have been evaporated by Hawking radiation. But anything from that scale on could be possible. If it is a particle, you know, theoreticians have a very good imagination, so we have a very pretty good ideas. We have 22 orders of magnitude spanning mass the particle can have. Can be very, very heavy, can be very, very light, can be produced in the early universe in very different ways, and each of these can have widely varying interactions. Some are more theoretically motivated, some more ad hoc, just to explain the problem of dark matter, but there are plenty of opportunities to look for new particles, because we have to extend the standard model. Then we can look at that at accelerators, so we can produce them. If they are heavy enough, we can produce them at high energy interactions in accelerators and see imprints of these new models of the presence of new particles. This is CMS and this is Atlas at the Large Hadron Collider in Geneva. Or if they are very light, like axions or axion-like particles, they can actually either convert in a magnetic field into radiation, or can actually decay into photons, and therefore we can have different ways of looking at these particles. These are some experiments. They're trying to look at these particles, which are actually very light. The previous slide was referring to particles that have masses, let's say, from the giga-electron volt on. These are particles that might be definitely smaller than the electron volt scale, very light, even micro-electron volt, or even lighter. Therefore, we don't know what dark matter is, but there are a lot of theoretical and experimental efforts. And the last thing that I want to say is that if the dark matter, if what forms the cosmic web, what's inside the galaxy cluster, what's inside the galaxy that we do not see directly, but we infer the presence of that, it's a particle, it will do something. The galaxy is a large object. There is a lot of dark matter mass here. Even if it is rare, the probability of having two particles interacting, or one interacting with magnetic field and doing something, or decaying and so on, it's not that small. It's small, but not that small. And therefore, we could have objects which are standard in the sense that we know they exist, like neutrinos, photons, antinucleon, electrons and positons that are produced by dark matter, for instance, in our galaxy, or in another galaxy, or in the whole universe. And this messenger come to us, and we can measure and maybe infer information of the fact that that particle have been produced by dark matter. There are a lot of possibilities in with any kind of message. It can be gamma rays. We can look at in gamma rays, in X-rays, in neutrinos, in radio, also in infrared. Maybe it's not written here. And then there are even other ways, depending on the type of the particle. So there are many, many different options, and these are actually exploited. Just to give an example, if dark matter can self-annihilate and produce gamma rays, what we would actually see is not radiation in visible light, but a glow of gamma rays, a cluster of galaxies glowing gamma rays. We don't see that. And this is because dark matter is dark, in the sense that the probability to produce enough radiation to see a glow at the moment is actually not possible to see that. But there are attempts to look at that. Clearly, there is no conclusive evidence in any direction. This is not occurring in nature, or this is actually occurring in nature. For instance, if we look at the satellite galaxies of our galaxy, which are small but close, we don't see any excess. But if we look at the galactic center of our own galaxy, we see an excess of radiation in gamma rays that could be related to dark matter. There is definitely a correlation between gamma ray emission and the distribution of galaxies as a whole in the whole universe, with the lensing measurement of the distribution of mass in the universe, even with the CMB lensing and with the clusters. The point is that this correlation refers to gamma rays that could be emitted by dark matter, but also by some boring astrophysical sources. So this we don't know at the moment, but features are different from what dark matter can produce in astrophysical sources. So this is an active line of research that tries to get all kind of information, some particle physics information and some gravitational information to actually put everything together. And from the experimental point of view, there are a lot of different options. Now, in the infrared or optical, Hubble, fortunately, is still flying, but the James Webb Space Telescope has been launched and now it's operative. Gamma rays with a Fermi-Lat satellite. This is AMS, magnetic spectrometer, which is actually this object here on the space station. This is measuring antimatter, even gamma rays, but mostly antimatter coming through space. These are radio telescopes. There is a lot of effort in developing big arrays of radio telescope, also single dish, but mostly arrays like square kilometer array or VLA, Atacama, and so on. These are actually detectors that can measure very high energy cosmic ray impinging on the high atmosphere and producing showers of radiation that then is measured. This is actually a gamma ray telescope that measures gamma rays at energies higher than that. This is a satellite, this is on ground. This is an inner photographs of these are the photomultipliers, and inside of this cylinder that is, there is water basically. This is seen when it's empty. And this is the super Kamiokande detector. There is the hyper Kamiokande detector which is being built, and this sees neutrinos. This is the ice cube detector at the South Pole. This is actually the outer part, but the real detector is below the ice, inside the ice. It's kilometer cube size, sort of. Then there is the kilometer cube net, which is a similar idea, but this is actually one module of the many that are digged now in the Mediterranean Sea, close to Sicily. This is kilometer cube net. Then we just received the data that are now under analysis from this experiment, which is called GAPS, which measures antimatter, and this is being launched from Antarctica. This is a balloon flight. It made 2 orbits around the South Pole, and then it was recovered, and this can measure antimatter at very, very low energy. And then, of course, there are experiments underground. This is the underground laboratory in Italy, in Gran Sasso, but there are many around the world. And we need theory, of course, and computing power. Computing power is getting actually quite relevant because the amount of data that are coming is actually increasing significantly in this field, from cosmology, astroparticle probe, multi-messenger probes. I didn't talk about gravitational waves, which could be also a way of looking for dark matter information, and therefore the field is actually quite active, and maybe at some point we will figure out what this dark matter is. And then remember also that there is dark energy, but this is another chapter. Okay, so thank you very much. I can stop here.
It's a very simple question. Before, in the graph that you showed of the composition of the pop, there was a 0.005 black holes. My question was, why black holes should be separated from the atomic matter or baryon matter if they are they collapsed after the Big Bang nucleosynthesis?
Yes, I mean, we have atomic matter is fixed by Big Bang nucleosynthesis comparison with measurement of primordial nuclear abundance. It's not like helium. Black holes, primordial, okay, there is this number which is very likely referring not to the primordial one, because primordial one could in principle be this 25%. A black hole that is formed after Big Bang nucleosynthesis actually counts as normal matter, as atomic matter, because it was a star collapsed into a black hole, in a sense, no? The point is that if the collapse to black hole occurred in the early universe, the early phases of the universe, before Big Bang nucleosynthesis occurred, this does not count as baryonic matter. You could even collapse radiation, not necessarily non-relativistic matter. If they are very, very early time and the universe was very, very hot, as long as you have a perturbation that enters the horizon and it's significantly large enough, it can collapse to a black hole. And they don't count because they do not perturb Big Bang nucleosynthesis, which tells you that you have roughly 25% in mass of helium in the universe, primordial origin, and this is directly related to how much baryons we have in the universe. And therefore, if everything that happened before the collapse to black hole before does not count, because it does not perturb that.
Well, I have a question.
Yes.
So in this big landscape of possibilities, where would you put your money?
I was asked the same question by the president of commission to INFN. And I, of course, evaded the answer.
But here,
If I would have infinite amount of money, I would put money everywhere.
sure,
Then your question is if I have not infinite amount of money. That's difficult. That's difficult. I would not actually. I mean, maybe it gets a little bit technical for some of you that are not expert in this, but there is now this big debate: WIMPs versus axions, right? Because heavy particles called WIMPs have not been discovered up to now, but neither axions, I would say. But since axions are less studied, axions, and they have a very nice, interesting phenomenology, people say, okay, WIMPs they do not exist, we have to look only to axions. I would try not to do that, in the sense that you still have possibility to explore, at least at large. You don't need to go to very fine details until you find a signal which is compelling. Therefore, I would try not to close everything from one side and not go to the other. You know, gravity acts in the same way, in a sense, at any mass. Therefore, it does not help us in saying you have to go to this range of masses or this range of masses for the dark matter. If possible, I would try to keep at least development in at least a couple of directions. And something comes from other type of studies. Not necessarily you have to dedicate an experiment to that specific topic. Some of these experiments are actually also useful to do something else, which is maybe the most rewarding thing that you get. For instance, if you look to gamma rays from dark matter, you end up doing a lot of astrophysics that was never done before. So if you build a detector, for instance, now Fermi is actually going to be discontinued at some point because it's very old. It's in space since 20 years, I think. So, but to close that window, to say we don't go on for that, I don't think it's wise. Of course, it depends on the cost, no? But sometimes the cost of some of these experiments is way less than something else that we do in the world. Maybe you understand what I'm saying. So I would actually try to go on. And then you can do a lot of other things, understand better astrophysical sources, for instance, then might be helpful for you to pinpoint better if there is a signal of dark matter or not. So I would not just go in one direction. Then I understand that money is finite and therefore, but yeah, difficult to answer. Passiamo.
Okay. I have a question about, everyone talks about dark matter, okay?
But in this pie chart, the dark energy is more than 70% of the universe. So I haven't seen no one talk about the dark energy part. So what's the reason?
In my talk,
No,
time constraint. If you want, I can go. I have 58 slides. No, the question is why people study less dark energy than dark matter. Well, dark energy was sort of discovered much later. No, dark matter is a long-standing problem, even 100 years, even though for the first 50 years people were not really crazy about that. And then, but it started earlier, even from the point of view of experiments, underground experiments, satellites. Dark energy was basically discovered at the end of the 90s, and there is one simple solution, which would be maybe boring to most of us, but it's a simple solution. The famous cosmological constant. The famous cosmological constant in principle works. Why not another fundamental constant of nature? That's a solution. Then there are actually nowadays, there are actually many studies around the way to produce what we call dark energy, which is basically the fact that the universe expansion is accelerating, and we see the acceleration not from any time in the past, but from some time on. This is a sketch of this is a size of the universe that increases, no, in dimension, and if you only have matter, gravity attracts, so you would expect that it slows down the expansion. But at some point, basically half of the age of the universe started to accelerate, and this cannot be none other than some exotic stuff. There are many ideas. The point is that to study experimentally dark energy, the first thing that you need to do is to map in a more finer way the distribution of what is in the universe, which is again what you see. For instance, this is a daisy map which has a much more galaxies, and from the structure of this pattern you can infer information from the voids, from the filaments. Or I didn't talk about baryon acoustic oscillation that also tells us information. So if you map much better, then you can maybe Euclid satellite is actually built to study dark energy in a sense, no? Also DES and DAISY. And these are actually experiments that go in space, map distribution of galaxies, which is a technique which was done already before, so it's not something completely different. For dark matter, you have a very wide different type of experiments, because if it's a particle, you can have many different types. Accelerators, gamma ray detectors, radio telescopes, X-ray detectors, and so on. So maybe it seems that there is more activity. In doing that, the main object to make a new X-ray detector is not to look for dark matter; it's to look for anything that emits in that band, no? But then you also have that. So people are actually using a lot of much more information to try to dig out the problem of dark matter. From the theoretical point of view, now there are many ideas. I mean, dynamical dark energy, you have one or more scalar fields evolving. A lot of that is done where the scalar field is actually related to an axion-like particles, maybe a very light one, that has some dynamics in the universe that can induce this acceleration. Or you have the part of modified gravities and so on. So yes, maybe the perception is that there is less study, but it's actually also increasing. The problem is there is no way. So either we made a mistake, that's a possibility, but it's difficult because there are many different inputs that tells you that you need to have that component. And okay. There are also experiments in the lab that could help, but it's more easy to look for a particle in the lab than to look for something that it's very likely not a particle. It can be a field, but to measure a field which has not particle excitation, maybe it's more complicated. So, especially if it is a 10 to minus 32 electron volt field, which is very strange. So yeah, so it's more difficult to build an actual experiment to look for that. So the main part is to look at the large-scale structure of the universe and try to see. The main point now is to understand if what we call dark energy is a constant or it's dynamical. So it's something that changes with time. And some recent measurement can even have very weird results. So even phantom-like type of dark matter, which has a very strange equation of motion, so on. So this is the path for the moment for that.
So I know that in cosmology we usually talk about cold dark matter, right? So I was wondering about the particle aspect of dark matter and if this cold property was very useful to constrain a lot of models. And second question, are we near to another property that we are discovering about dark matter, phenomenological property, like being cold?
Like being cold. So for the coldness, coldness means that it's cold, so it acts as cold at the time of the onset of structure formation and during structure formation, which is a little bit I mean, let's say, well, it depends if it's a particle. Okay. The actual time, it depends on the type of dark matter particle. So the coldness can be realized in different ways. It can be a heavy particle which decouples, the WIMP, no? It decouples when it's non-relativistic, and therefore it remains non-relativistic, and then it will start. But this is one way. Another way is to have a scalar field, like the action, which has some strange dynamics in the early universe, and when a scalar field is actually oscillating around its minimum, it behaves exactly as matter. And therefore you can, what we call cold from the structure formation point of view is something that does not, technically is what is called, does not have a strong free streaming. You want to compactify matter in a given volume, which is the galaxy. If the particles are relativistic, they just don't want to stay there, no? Photons, it's not easy to compactify photons. So if you have a particle that is too relativistic, you cancel out fluctuations at small scales. So it's the effect that we call cold. Then how do we realize that with a particle? In different ways. That's the point. You can have, it's a real cold particle, non-relativistic particle. It's not a non-relativistic particle, but it's something that behaves as, from the point of view of gravity evolution of a universe. So, yeah, so, okay. Then the second question was if we have other properties that, well, we need that it has to be cold because otherwise that simulation that I showed you that reproduces well what we see does not work. It needs to interact not much with anything else, so the so-called weakly interacting is a necessity. The bullet cluster is a sort of more direct evidence of that, but then there are other arguments in favor of that. Therefore, you cannot have something that interacts too much. Otherwise, it would work more like baryonic matter. Then what else? It's difficult to say because the point is that you need to find a feature that acts at cosmological level that is actually typical of something that is a particle, like coldness or type of interaction. So I don't have something that comes to my mind now, but maybe after the wine, which is baryonic, by the way.
Very good. I think we can thank the speaker again and go for the